All right, so we've been talking about some awesome stuff today, looking at some deep dives into Wi-Fi 7, looking at band steering, but now we get a little bit of a palate cleanser. We go back to the fundamentals and look at some RF. That's where it's at. So we're going to look at why polarization matters in your environment and why sometimes maybe it doesn't. So to start, we kind of have to understand, for some of us, what the actual form of your wave is. So simplest way to describe your signal is as you have your antenna element and you pass your current through it. That'll actually create the EM wave, and this can be represented as a sinusoidal wave passing through the air. There's a couple of variations of this. It can be linearly polarized, so that pure sinusoidal wave that you can imagine. That can be vertical, horizontal, negative, plus 45, but it can also be circular. Circular is typically not used within Wi-Fi and cellular. That's not because it isn't good. It actually, in a lot of cases, is better. It can reduce multipathing. But just out as a curiosity, how many of y'all recognize these graphics? Anybody? Good, you should, because it's part of the lab for the CWNA, so we should all be familiar with these. But beyond just having the single polarizations that we're looking at, there's also dual polarization. There's a lot of benefits to this. It can make you less susceptible to interference in your environment. It can improve your SNR. It actually helps on MIMO because it increases port-to-port isolation of the actual elements. And there's the obligatory, it depends there, because it depends on your environment for a lot of those things to really take effect. And really the main drawback that you get when you're implementing this is that it complicates your antenna design. So if you have a asymmetrical directional antenna where it's 120 by 15 degree beam width, for instance, you have to redesign each one of those elements then to be able to match that propagation and then be the correct polarization you're looking for. If you're designing an antenna that's symmetrical beam width, it's not nearly as bad. You can physically rotate the element inside your radome, and then that'll affect the polarization. So it kind of depends there as well, but the main reason why you don't see this on every antenna out there is depending on its propagation and its design, it can complicate it, which in the end increases the cost for the user. So a question I often get is, why don't we do more than dual polarization? If you get those benefits from it, why don't we go to quad polarization, or if you're using an 8x8 antenna, why not octuple polarization? And the main answer to that is it's just compounding on the effects that we just talked about. So it does give you some improvements into your SNR and reduces interference, but it's diminishing returns. The main benefit of the initial dual polarization is that your vertical and horizontal, or plus or minus 45, those two signals are orthogonal to each other, they're right angles. So there's very limited interaction between those signals. Well, as you add more and more polarizations towards plus or minus, then you start to be able to hear those adjacent signals that aren't actually orthogonal to each other. So you can do this. There are plenty of vendors out there that do have quad polarization or further polarization antennas, but it just gives you diminishing returns on the benefits while drastically increasing the complexity of the actual design. Going back to kind of something I mentioned earlier, is the physical orientation obviously significantly affects this. So if you can physically rotate the antenna element inside the radome, you can equally physically rotate the antenna as you deploy it. So if you have an antenna that's linear or vertically polarized and you rotate it 90 degrees, that's now a horizontally polarized antenna for all intents and purposes. And this can be done for 45, minus 45. So you just kind of have to know what your antenna is and what you need in your environment, because maybe you want a plus or minus 45 degree polarized antenna, and you can do that by getting a specialized mounting solution and just making it to where it fits in that new physical location. The other obvious component of this is, what is your client device doing? So if you can physically manipulate the transmitting device, what about the receiving device? So having your different devices, whether it be a MIMO device or a SISO device, obviously affects this, but we're going to typically be looking at MIMO devices for this, because most things nowadays have gone to that. And particularly, we're going to be looking at the iPhone and iPads. So these are pretty ubiquitous across the board. Everybody has these in every deployment, whether it's warehousing, schools. It's going to be pretty good representation of what we'll see. So the antenna arrays on the iPhone are spread out across it. There's full tri-band radio on the bottom for the iPhone 15, and then it's kind of split up on the top. And I actually went in and looked at the internal specs for this. Shout out to Jan Jones for working with me on that. And we discovered that the antennas for the Wi-Fi elements actually are at least only vertically polarized. They're not dual polarized, which I thought was pretty interesting. So to get a good test of this, I went out and did an AP on a stick test. I just had a completely vertically polarized antenna, put it about 15 feet, go about 75 feet away. Also, to do this test, I used the WLAN Pi Pro in bridge mode. I don't know if any of y'all have done that, but that's actually a really great way to do AP on a stick tests. Just a quick shout out to them. And before doing that, though, I just was kind of curious. Okay, so we have our client devices that we typically use, but what about our survey devices that we always use? So I grabbed the Sidekick V2, and I held it at the same position for everything, held it completely vertical, turned it sideways, and then held it flat towards the actual antenna. And as you can see here, it actually did pretty the same on the two vertical orientations, whether it was rotated to the side or not. So that was pretty good. That's how you want it, because you're typically going to have it at your side. But holding it flat, it obviously had a pretty significant drop on the 5 gigahertz receive signal. There's basically a 10 dB difference between the designed way it's supposed to be orientated on your hip versus being flat. So unfortunately, if you're going around a warehouse and trying to get away from your body attenuation, you can't wear it as a hat to do surveys. But and then I was kind of curious, because the Nomad had just come out, what was it like? And we can kind of see the same results here. It was great and pretty consistent across the board in the orientations that you'd expect to have it while you're doing a survey, but if you put it flat, it's not going to receive the signal nearly as well. But now the main thing, so the actual client devices that we're using within these environments. So the iPhone and the iPad, the two devices I tested, the iPhone was just an iPhone 11. It didn't have the 6 gigahertz for it. But it actually did the best when it was in a flat position. So in this way, the antenna was facing towards it, so it actually received the signal best if the top of that phone was in the direction of the antenna. So that was interesting, because if you're taking phone calls or if you're in a typical building with APs on the ceiling, that vertical position is the better position to have it in, which makes sense if you're doing voice over Wi-Fi. The iPad, however, was pretty resilient in whatever position you had it. There was only a couple dB difference across 2, 4, and 5, no matter what orientation you had it in. So I didn't get the specs for the internals on that. That one may actually be dual polarized, but it was pretty resilient overall for that. And why do we see that? Because if it's a vertically polarized antenna, it should be a significant drop-off for the singly polarized antennas within the actual iPhone. And the reason is in the real world, we have reflectance. If we were to redo this test in an anechoic chamber where it was completely absorptive in that environment, you didn't have any reflectance, we'd see very different results. But we don't live in the real world, so whereas here, if we didn't have any reflectance and you had two orthogonally polarized devices, you wouldn't receive any signal or receive a very poor signal. But in the real world, we don't have that. We do get reflectance. We do still receive some signal, because it's not always going to be orthogonal to all the reflectance that you experience within your environment. There is some caveats to some of this, just depending on your environment and what devices you're using. And we didn't even touch on point-to-point, which is a completely different thing with polarization. But if you want to get more in the weeds on that, I'd be more than happy to talk to you on the side. Thank you.